Broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. I'm Woody Cash, SCT Content Officer for the Golden Gate chapter. Welcome to day 2 of the All California Chapters Training Summit. Yesterday's topic was SFP transceivers and was presented by SoCal chapter. Tomorrow's topic will be VMCTS presented by the San Diego chapter. And Thursday, the Sierra chapter will be covering FDX. All sessions begin at 8:30 local time. After each session, we will have a virtual tabletop and our raffle. So just a couple notes on chapter business. Elections start next week. Please take time to vote for those who are running so we can get a good board for our next year. If there are any training topics you would like to see presented in 2025, please email them to woody_cash@comcast.net, and I'll try to work those in. So I'm just going to take a second to promote SCTE. If you're not a member or not a chapter member to your local chapters, please take a minute to join. A lot of us have Cable Labs All Access, so membership is free to many. But with that membership, you also get access to standard publications, white papers. You can participate in things like cable games, and there is just a load of online training, including archived webinars. So we can jump to today's topic. So I apologize for any confusion. We had one name in the registration, but we came up with a different and more applicable name. And that is qualifying network performance and impairment priority in modern DOCSIS networks. So there's going to be some changes in the way we approach things. So as we start deploying DOCSIS 4.0, we need to rethink how we approach network maintenance. We previously prioritized our work based on customer experience, but adaptive modulation profiles will require a different approach to plant fault prioritization. And we have two of the best presenters today. Sorry, don't mean to embarrass you guys, but I think you are two of the best. So
no, I agree. I think Paul and Larry are rock stars.
So today's presenters will have Michael Dell and Larry Wolcott. Mike is a distinguished engineer, and Larry is engineering fellow at both with Comcast. Even with these lofty titles, Mike and Larry are very talented, and most importantly, they have the ability to relate to and take feedback from those doing the work. I think that is where they're really the rock stars. They like to know how it impacts these changes and things that they do impact you. So that's very important. And so after the presentation, we're going to have a virtual tabletop with Paul Shea, who's going to talk about metallic TDRs. We'll also have a raffle. So don't hang up immediately after we end the presentation. Hang in there for a few minutes, and we'll tell you something about metallic TDRs and try to get you a raffle prize. So hang on for that. And with that, I'm going to turn it over to Mike, who's going to be our first presenter. Thank you, Mike.
Awesome. So I do want to jump on the Springbok bandwagon and say, if you have a chance to win one of their coffee cups, they're fantastic. And also to mention that we at the Penn, Ohio chapter have had a really good relationship with all the folks at Springbok, and we posted some MTDR training videos on our YouTube channel with Springbok and Chuck Phillips there. So, all right, I will be very, very brief in my beginning here, so that Mr. Wolcott doesn't beat me up again. But thanks for having me today, Woody. We talked about this a little while ago. The genesis of this was actually for our SCTE presentation, where I had the joy and pleasure of presenting in a panel at SCTE, and that panel was called "Your Network is Talking, Please Listen." So in that panel was Mr. Larry Wolcott, the distinguished fellow that Woody introduced, and Bilal Hamza, talking about tier-based bonding groups. I think is going to be really fascinating, especially for the Comcasters as we go into FDX. So I think we may have to come back and talk about that one with Bilal another time. But my presentation, and I'll go ahead and start sharing. Can you see my screen?
Not right now, Mike. Oh, there you go.
All right, awesome. So let me go full screen here. We got it full screen?
Yes.
All right, so as Woody mentioned, the name of the presentation is more lean toward priority, but I really want to start with why we want to prioritize differently. And in order to do that, we have to start talking about efficiency. Now, efficiency isn't new, and I posted a couple of definitions of efficiency here from different places. The one that I like the most is, actually there's a couple. The Cambridge Dictionary says the quality of achieving the largest amount of useful work using as little energy, fuel, effort as possible. And then the other one is the ratio of useful energy delivered by a dynamic system to the energy supplied to it. Now, I really like this definition because of the two words dynamic system. Okay, now the concept of efficiency is not new, right? We recognize that almost all machines or systems are designed to be as efficient as possible. The graphics on the screen, one of them is the windmills in the top right-hand corner. Now, windmills have been around forever, and largely because there's very few moving parts, and it allows the efficient transfer of that wind energy into useful mechanical energy using the windmill. So they're relatively efficient. That's why they've been around for so long. The machine at the bottom is actually a prototype for a patent for an envelope folding machine. So you can see that thing has a lot of moving parts, a lot of ways that it can break to try and fold an envelope. That's from the late 1800s or early 1900s. So there's a lot of different machines. When you go to buy a vehicle, for instance, there's typically some data around the fuel efficiency. And the things that go into the fuel efficiency are the weight of the vehicle, the amount of horsepower, the aerodynamics, all of that kind of thing. When you buy a refrigerator or a heater, there's efficiency ratings on those as well. So efficiency as a concept is not new, but we don't really talk about efficiency in the context of cable television systems, or particularly DOCSIS networks. So speaking of efficiency in DOCSIS networks, there was a white paper that came out, I think in 2021, called Improving DOCSIS Efficiency, published by Cable Labs. And this was really in response to the impact to the networks caused by COVID. We gained, I think I heard 3 years of capacity in 6 months or less. So when we think about the efficiency in DOCSIS, we really leaned into this back in 2019, 2020, and into 2021 when this specification was published. And I think Larry contributed to it. There's a lot of really good information there to talk about how to get the most out of your network, and particularly on the upstream. A lot of networks had downstream bandwidth that they were able to leverage by moving some linear video channels around and adding OFDM to try and add more downstream capacity. But on the upstream, it was a lot of cases bandwidth limited, a lot of sub-split networks out there still. And so this report really did a good job of saying, hey, here's all of the knobs and levers, much like this aircraft cockpit, that you can get in and configure your DOCSIS network on the upstream, including SC-QAMs and OFDMAs on the upstream, or SC-QAMs or OFDM on the downstream. But it really leaned heavily into the upstream. Try and get more data through the same pipe as measured in bits per second per hertz. Now, this is going to be important as we talk about efficiency. But you can download that if you're a Cable Labs member. If you're not, we can make that available to you, this Improving DOCSIS Efficiency paper. It was very informational. So efficiency isn't new in the energy space either. And I alluded to this at the beginning. A lot of things that you buy these days, electrical appliances, are really valued for their energy efficiency. And even in cable television networks, energy efficiency is very much front and center. We look at power consumption of the outside plant here at Comcast in a unit called energy per consumed byte. And so there's other metrics when we talk about data centers or critical infrastructure or other places. There's different RF metrics or different energy metrics that are applied to energy efficiency. We'll talk more about energy efficiency as it pertains to RF performance later. Okay, so let's talk about modern DOCSIS networks. There's been a lot made about DOCSIS 4 and already talking about DOCSIS 5 about our ability to deliver symmetrical speeds over coax. And I almost can't say that without giggling. And I've had this problem for about 3 years since we actually tested and deployed a network that was capable of delivering symmetrical gigabit speeds over a coax. Because if you'd have told me 10 years ago that we'd be able to do that over our traditional HFC networks, I probably would have called you a liar and laughed you out of the room. But here we are, we're delivering multi-gigabit symmetrical speeds over these DOCSIS 4 networks. Now, there's different deployments of DOCSIS 4 that are both capable of achieving the end goal, which is, more data throughput in both directions for our customers and symmetry. But the way to do it is different, and you may see that depending on which operator you're working with. So here at Comcast, we're deploying what's called full duplex DOCSIS, or sometimes known as FDX. Other operators may be using something called frequency division diplexing or duplexing, also called extended spectrum DOCSIS. So you may hear the terms ESD and FDD. Those typically still contain a diplex filter. It just moves from 42 megahertz up to 200 or higher megahertz for mid split, high split, or ultra high split. But there's typically still a diplex involved, which is why it's called frequency division duplexing, or ESD. It also is predicated on the premise that we can extend the upper band edge from 1 gigahertz out to 1.7, 1.8 gigahertz, possibly 3 gigahertz, or even farther in the future. Now, there are a lot of differences between those two, but there are also some shared assets. When you look at the frequency allocation of 1.2 gigahertz full duplex, you can see on the upstream you have your dedicated mid-split spectrum, and then this portion of spectrum which is dedicated to either upstream or downstream in full duplex, and you can see the overlap in the downstream that goes out to about 1.2 gigahertz. This would be the portion of this would be dedicated downstream. The other portion would be shared spectrum in FDX. Now in ESD, you still have the dedicated upstream from 5 to 85 mid-split, and then potentially the extended spectrum here that is still diplexed, which is why this portion is whited out for upstream growth out to potentially 684, and then the downstream would shift then out to potentially 1.8. So there's a lot of shared assets between the versions of DOCSIS 4 that are important to note, whether you're deploying FDX or FDD. We also have to recognize that we're operating today in a very hostile over-the-air environment. And particularly as we expand our upstream bandwidth. Most of us that have worked in the field for any length of time, particularly in two-way operations now for the last 25 plus years, a lot of our time is spent managing the upstream noise floor, because that spectrum 1 was limited, but 2 is very, very valuable. And as we expand that upstream, what we're going to find is that we're going to encroach on the frequencies that are allocated to over-the-air broadcasts and other things that we didn't really encounter before in the upstream. Now, I will argue that these things have been here all along, but we really didn't look at them or see them because they were under the single carrier QAMs and linear video or other things in the downstream. But as we start to expand our upstream, this is a mid-split system. You can see there's 2 over-the-air VHF channels in this portion of the spectrum here. And as we go out to high split, you'll see other things. Now, we are trying to avoid FM, but it's very real. FM is everywhere. And in this high split upper channel, you've got, NOAA's in here. You've got other UHF and VHF channels. But when you look at the entirety of the spectrum, there's a lot of over-the-air energy. Now, it's important to understand your particular environment because every geography has a slightly different over-the-air environment. I will say it's probably still hostile, but if you're in a major metropolitan area, I would challenge you to take an antenna and a spectrum analyzer and go out and look at all of the energy that exists in your over-the-air environment. Because what I think you'll find is there's a lot of stuff out there that is occupying the same band or frequencies as our traffic. And as we increase the upper band edge of our spectrum, we're going to run into more of these. And as we increase the upper band edge of our return, we're going to encounter some energy that we historically only saw on the downstream. And in some of those cases, it was more of a binary relationship. So imagine if you had VHF ingress in the 200 megahertz area that was getting into your network. Historically, that would have been linear video. It would have caused a bunch of video tiling that generated trouble calls fairly immediately. And then we would have gone out and addressed that through the normal maintenance escalation processes. So imagine now that's in the upstream, sitting under these carriers, that binary relationship to the customer experience isn't there anymore. So let's talk about that. More and more of our networks are leveraging something called PMA or profile management applications. There have been a couple of really good SCT papers that have been written on this, going back to 2020. An engineer at Comcast called Maher Harb wrote a really good paper on automating that in 2020. And then there were some machine learning models that were developed and for a paper by Comcast Jude Ferreira in 2023. So if you have the NCTA link and you can look up those papers, they're really good papers. I recommend that you read them. So I'm not going to boil the ocean here on PMA, but what's really important about it is they've become an operational prerogative. We just talked about the hostile environment that our network operates in, and it's nearly impossible to keep all of that out. Now, we have really good practices around leakage management and repairs, and automated tools that tell us when we have poor signal quality that's driven by ingress or other noise. But we have this profile management application at Comcast that's called Octave, where we measure and collect data on all of our upstream and downstream interfaces, and we store those, and then they get analyzed, again, going back to some of the machine learning models developed by Jude and other people that identify patterns, make recommendations to optimize the network, i.e. reduce the modulation profiles in a certain frequency band, and then request change events to the CMTS, which updates the configuration into the cable modems, and then we start that cycle all over again. And so what happens is, in response to impairments, the system recognizes that there's an impairment present or that there's signal quality degradation in a portion of a channel, makes recommendations then to the CMTS configuration management system, which then changes the modulation profile for a channel or a portion of a channel. Going back to the Cable Labs document around optimizing DOCSIS efficiency, is within OFDM and OFDMA channels. Those could be, very large blocks of spectrum from 48 megahertz to 192 megahertz or beyond. The entire channel doesn't have to change. only the affected portion of the channel would be updated to have a lower modulation profile in response to the impairment. Now, the great part is that the customers don't feel it. This is automated and it's very reliable, so that when the impairment happens, the system detects it, it makes the change, and the customer impact is negligible, if at all. Awesome, right? Well, kinda. Okay, let's talk about the historical characterization of a network. For many years, we have relied on the signal quality metrics of the channel relative to the channel's type. Back in the days when we had analog video carriage channels, we would measure CNR, CSO, CTB on the analog channels. Along came digital. Now we begin to measure MER or RX MER, sometimes called SNR. On the data integrity side, we measure BER, bit error rate, and or code word error rate. And then lastly, on the transmission medium response, we would measure frequency response. So you can see this is a very lovely water wave on the downstream, and on the upstream, we have this in-channel frequency response issue here. So we've gotten really good at measuring the impact of an impairment to a particular channel type, whether it was a QAM channel, 64 QAM, 256 QAM, some cases OFDM. We can see this RX MER dip here that would indicate that there's some ingress in this portion of the channel that's affecting this particular band. And so programs like Octave or other profile management applications in response to this could suggest that the modulation profile of the mini slots in this region be downgraded because the signal quality is poorer. Now, I say all that to say this: much of our tooling over the last 20 years has been built with thresholds in response to these things. So we'll see impact or events for low receive power or low MER or high transmit power, low SNR, things like that. Now, some of those thresholds are still valuable, particularly around the transmit power and the receive power, but I would argue that the linear relationship between SNR and customer experience has been broken by these profile management applications. Before profile management applications, when the system began to degrade, you could see the trend when your SNR started to decline. And let's take, for instance, upstream ATDMA SC QAM channels. For those of you that have been around for 5 years or more, pre-Octave, which has been running now for 3 to 4 years, believe it or not. When your SNR or MER on the upstream started to degrade, you would notice an increase in correctable errors or correctable FEC using Reed-Solomon error correction. If the SNR or RX-MER continued to degrade, the impairment was more severe than what the Reed-Solomon error correction could fix. Therefore, you would begin to take failed FEC. And that's when we really built that threshold that says, hey, if we start to incur failed FEC, that's impactful to the customer experience, and that's a demand maintenance type of activity. So as these profile management applications come online, they measure and monitor the reduction in SNR or RX-MER and recognize the incremental increase in correctable FEC, and in many cases can make a profile change before incurring any failed FEC. So that relationship between the SNR trend and the actual data integrity, meaning failed FEC, that related to the customer experience has been broken. So how do we rationalize then the severity of an impairment when the customers don't feel it, not necessarily from a customer experience perspective, but from a network prioritization perspective. So in order to do that, what I'm proposing with this paper is that we begin to think about the impact of impairments differently and not focus on solely the legacy metrics of SNR, RX, MER. Instead, we would measure the impact of those impairments on the efficiency of the network itself. Now, I'm not asking us to stick our heads in the ground like an ostrich and ignore impairments. That's not the case at all. What I'm suggesting is that we look at the impact of the impairment differently. As I mentioned, the historical relationship between RX, MER, SNR, and correctable effect is broken. PMA, in some sense, has masked spectral impairments because the impairment itself is no longer customer impacting. Therefore, we don't see the normal transactional relationship between the impairment and the customer, i.e. trouble calls and network escalations. Now, the other thing that I would argue is the incremental bandwidth as we've expanded into mid-split, high-split, and FDX, we've increased our operational capacity in both directions, right? So when we measure by capacity, we have this false sense of security because we now have more spectrum. In some cases, we have more efficient spectrum in OFDM and OFDMA as opposed to SE-QAMs in the upstream or downstream. So we have the perception of spectral efficiency because we've added capacity, but we're not really measuring the relationship between the impact of the impairment itself to the actual capacity and spectral efficiency. So here's just an illustration of that historical linear relationship between SNR. As it goes down, correctable effect goes up, failed effect goes up. Okay. So I want to be eyes wide open about this and say PMA systems are great. PMA and Octave, particularly at Comcast, is one of the coolest things that I've had the benefit to work on and to watch work to mitigate the impact of impairments to our customers over the last 3 to 4 years. But when we think about impairments, and we need to begin to rethink how we process them and also prioritize them. So I will say, analogous to medicine, there's a very distinct difference between health and medicine, right? If you're focused on eating healthy and exercising and all of the things that your doctor tells you to do, and maybe you do, maybe you don't, versus living an unhealthy lifestyle and then going to get medicine to treat the symptoms of the ailments, rather than treating the root causes. Similarly, in the cable networks, we have these symptoms that we measure all the time. And our tooling does a very good job of that, whether it's frequency response or data integrity or transmit receive level power, etc. But most of the things that we measure are lagging indicators. The problem has already happened. They're demand in nature or reactive in nature. And so we're proposing this thing called plant efficiency, which would measure the impact of impairments, but be a leading indicator and be proactive in nature and have a relatively simple measure of value. So as a measure of network impairment, plant efficiency can be independent and individually calculated on every node, regardless of node configuration. And we'll talk about that. On the downstream, we can measure OFDM channel efficiency using per mini slot or even lower per subcarrier modulation profile, and we'll look at that. On the downstream, SE-QAMs is a little bit different because SE-QAMs, DOCSIS QAMs in the downstream are relatively binary. They're either working properly, and in some cases, in many cases, you'll have a 256 QAM channel that is capable of delivering up to 38.8 megabits per second per 6 megahertz channel. Now, error correction in the current state, read Solomon error correction at the device, is very good at mitigating the impact of degradation to that particular channel right up until a point where the channel is too unusable and the device will put it into a partially bonded state and cease to use that channel. So we can measure some downstream errors on SCQuams, but we can more importantly measure the ones that go into a partially bonded state because the device recognizes the channel is too unusable and ceases to leverage it. On the upstream, we can use the upstream SCQuam channel efficiency. Now, the entire 6.4 megahertz channel, or 3.2 or 1.6, depending on your channel width, will be downgraded to a lower modulation profile using some of the techniques outlined in that DOCSIS efficiency paper so that it is more robust in the presence of an impairment based on current conditions so that your customers aren't impacted. On the upstream, the OFDMA, much like the OFDM on the downstream, can be adjusted using mini slots or even per subcarrier modulation profiles in the presence of an upstream impairment. Now, wouldn't it be great if we could determine a single figure of merit for the upstream or the downstream to determine how much of the channel or the network's capacity has been downgraded or lost because our profile management applications have made a change in the presence of that impairment? That'd be pretty great, wouldn't it? All right, let's play a little game called Which One Would You Fix First? So I don't know if I can see the chat or not, but I have 3 upstream spectrum captures using Comcast tool called Yeti. I would ask you to look at all of them, A, B, and C, and vote which one you would fix first. So Woody, I don't know if you can see the chat, but I can't.
Yes, I can see the chat. There's another question in there, but I did get, okay, I've got 2 people saying B.
B, okay.
I have another question also we can get to. Looks like I
Okay.
got more people chiming in.
Well, I'll tell you what, let's give them a chance to vote on this and go ahead and give
Okay.
me the other question. And,
Okay.
And we'll come back to the answer.
All right. So, question from Don Simmons. How does less effective modulation due to noise ingress impact data capacity? How does a MSO operationalize the fix of less efficient modulation driving a data capacity issue?
Wow, Don, the check is in the mail. So thank you for asking that question, because that is absolutely the point of this whole exercise. And we will get to that answer. But thank you for the question. That's absolutely the point of this exercise. All right, do we have,
so we have almost everybody's B. We have an A, and then we have a C, but everybody, 2 C's, but everybody else is B. It looks like the majority is selecting B.
All right. Now, thank you for that. Now, what I will tell you is that the answer in this one, based on this premise of plant efficiency being the prioritization engine, the answer is actually C. Now, I'll tell you why. When an impairment, then this goes back to Don's question too. When these profile management applications recognize an impairment, and in this scenario, take A, would have downgraded these 2 channels, as the modulation profile is reduced, so is the capacity or the available throughput. So from an inverse perspective, the lower the modulation profile, the higher or the more of that available capacity is then consumed. So in this instance, node A is actually average 48% utilization across the upstream. Node B is averaging 27% utilization across the upstream, whereas node C is actually 75% utilization across the upstream. Now, several factors come into play here. Obviously, the node size is important. So if this were a much smaller node with fewer devices demanding time and space in this upstream, the utilization would be lower, even though the modulation profiles had obviously been downgraded on multiple channels here. And in B, if this was a bigger node, then the utilization might have been higher and it would have shifted what we think the actual priority is. So all three of these are bad, right? They're impacted by some ingress or noise. But what I want you to begin to think about is, relative to the noise itself, how much does it influence the downgrading of the channels across that impacted spectrum? And what is that impact to capacity, or to the available capacity of the service group itself? Okay, we'll come back to that. All right, we'll play this game again. On the downstream, same thing. We have all of this OFDM spectrum out here and all of this DOCSIS SC-QAM spectrum in here. Which would you fix first, A, B, or C? This is a much tougher question.
Okay, I'm looking. Let's see, 908. Okay, so I do have some. I have one. I have a few now. So give me just another second here. We have a lot of participation, which is wonderful.
Good.
Well, we have a range, quite a wide range. So we have some B's, C's, a couple of A's, more B's, and a couple of C's. But mostly it's kind of like even between A's and B's.
A's and B's. Okay, excellent. The answer in this instance is actually C. Why? Okay, so there's no visible spectrum impairment in any of these, right? Except for maybe a little bit of reverse tilt in B. Now, in and of itself, reverse tilt isn't necessarily impactful to the customer experience, right? And the reason why C is the one that we wanted to choose, because there's actually 40 or 98% utilization in this downstream service group. Now, what you can't see is the ingress that's underneath of here that's resulting in these downgraded modulation profiles. The spectral performance itself looks perfectly fine, right? We don't see a ton of noise elevation. We don't see any ingress sticking out the top. So we're having to rely on the measurements that we're getting from our profile management applications and the impact of those to capacity. And that becomes the prioritization mechanism. So this one was really, really tricky. I'll grant you that. But in this case, C would be the highest priority because of the impact to capacity in this particular node. And these are true examples as of yesterday in Comcast network. So I wanted to go really, really quickly through Octave, our fast mitigate profile management application. And we referred to it already as to how it works, where we pull all of our service groups through our CMTS, publish them into a stream, goes through a data analytics process, makes change recommendation, which goes back to the change function of the CMTS and changes as quickly as possible. There's some rules that have been applied to the logic that says when to do it, when to downgrade, and then inversely when to upgrade. It's also relative to capacity. So in instances where we have relatively low capacity, we can downgrade farther and faster and say, hey, like, it's fine. We have all kinds of headroom for utilization and capacity. Go ahead and downgrade faster. When we have high utilization in a node, even at its peak performance, we want to downgrade quickly, but not as far, because the farther we would downgrade, the more it would impact capacity and drive up that utilization. Conversely, we want to upgrade faster on nodes that have high utilization. So if the spurious impairment goes away or a network technician fixes a problem, if capacity is high, we want to upgrade faster to those higher modulation profiles and buy that headroom back. Okay, We can also then measure the impact to the profile downgrade using a metric value based on a percentage of the available throughput that's been lost based on downgrade. So what we can actually do is calculate the total throughput on a per channel basis in a small increment of time, and then measure that against the utilization or capacity, in this case 80%, and come up with a value that says, how do we prioritize that, particularly in the upstream? Now, let's get into some examples of how we can calculate efficiency and why efficiency is important. As I mentioned, every node will have its own operational maximum, regardless of the node. If it's an active two-way node, we can go through every possible scenario. Let's say you have a 550 megahertz system. Some portion of that downstream is going to be allocated to downstream, and then obviously your upstream is fixed either at 30 megahertz or 42 megahertz, depending on your diplex. And you know how many channels and the maximum modulation profile of those channels can be calculated. So on a 750 megahertz subsplit system, for example, you could have up to 40 or more downstream SC DOCSIS QAMs at 38.8 megabits per second per channel. You can calculate the total throughput on the downstream of that. On your upstream, you're limited to 4 upstream SV QAMs. Now, I have Comcast Profile 251 is our highest modulation profile. That's capable of about 25 megabits per second per 6.4 megahertz channel. So you can calculate that entire upstream throughput as an operational maximum against which we can measure the efficiency of the channel. It's important to start with your operational maximum. That is the ceiling. If your node is running at its absolute impairment-free operational maximum on every channel in the upstream and the downstream, that's ideal. That is 100% efficiency from a plant efficiency perspective, right? And as we get into FDX, I have an asterisk here because there's a lot of caveats. There's a lot of nuance to calculating the downstream and upstream speeds that are available depending on the configuration of your FDX node. But suffice it to say, it's very, very fast. And so through all of these different permutations of upstream and downstream channels and DOCSIS QAMs, all of these can be measured and configured to say, this is what our operational maximum is. When we are impairment free and running at our operational maximum in the downstream or the upstream, we can think of the network, regardless of whether we see anything or not in our tools, meaning receive level, our XMER, frequency response, transmit power, etc. If we focus on the efficiency of the network, when the network itself is operating at 100% efficiency, then the capacity that is available to the customers in that particular service group is at its optimum. As impairments are introduced into the network, the efficiency will go down because of the modulation changes, and the efficiency also goes down, but more importantly, the amount of available throughput to the customers in that service group also goes down. And again, it's relative to the architecture in the node. So the capability of a 1.2 gigahertz FDX node is much, much greater than a 750 megahertz subsplit node because it's bandwidth limited. However, each of those nodes can be measured against themselves for their own operational efficiency. Okay, how does this work? So here's an actual example where we're measuring the efficiency of the OFDM downstream channels. Now, in this instance, there are two 192 megahertz wide OFDM channels. This channel, you can see these two white areas here. These have two guard bands, and those guard bands are there intentionally, and they're calculated into the channel's optimal throughput. Now, the highest efficiency that we can get out of this channel is 8.6 bits per second per hertz. That's at a 4K QAM modulation and 50 kilohertz subcarrier spacing. So we can actually measure what the operational maximum would be for these channels. Now, we measured the actual against the ideal. The ideal, is 8.6 bits per second per hertz, but the actual in this channel was 4.24 bits per second per hertz, which gives a total throughput capability for this particular channel of 542 megabits per second. That's only 49% efficient. Now, I'll show you the spectrum on this. There's actually a pretty interesting thing that happened to this node. But similarly, the 192 megahertz OFDM channel was running at 49% efficient. So the overall OFDM efficiency value is 49.6. Similarly, on the SC-QAMs, we talked about these being a lot more binary, where in this DOCSIS SC-QAM space, when channels are impacted or impaired, they basically go into a shut condition where the modem ceases to use them because they're so impaired. And we can actually calculate all of the devices inside of a node and all of the available DOCSIS downstream SC-QAMs and which ones are in a partially bonded state, and come up with an efficiency value for the entire downstream SC-QAM population inside the node. So we can calculate that. Similarly, in the upstream OFDMA, this is slightly different in what the ideal is. These are 25 kilohertz subcarriers, and so benchmarked against 4K QAM, 45.6 megahertz wide channel, our potential or ideal is 9.3 bits per second per hertz. Now, in this particular node, it was only running at 6.5 bits per second per hertz, which is about 70% efficient on the OFDMA. Now, interestingly enough, the same node, this was all the same node, by the way, in the upstream and the downstream. We calculate this already using our modulation profiles on the upstream. All four of the upstream ATDMA channels were running at 25.6 megahertz, which is 4 bits per second per hertz. So the ATDMA, or the subsplit upstream, was actually running at 100% efficient. Who'd have thunk it? Now, this is the node. So you can see there is some noise here in the traditional subsplit section, but the throughput of those modulation profiles was actually at its maximum, 25.6. But here's this VHF ingress from channel 2 and channel 6 residing under the OFDMA channel that was only allowing that channel to run at about 70% efficiency. You can see here there's some ingress in the downstream causing some devices to go into a partially bonded state through here, which is resulting in our downstream SC-QAM efficiency of 98. Now, on the downstream OFDM, this is where there was noise across the entirety of these two OFDM channels that was resulting in this really low modulation profile and low efficiency. So I'll fast forward through the business value of this, but obviously when you have systems that are self-healing and respond to impairments, the impairments themselves are no longer the primary indicator that there's an impairment that's going to require a truck roll or a network technician to go resolve, or even a premise technician. But when we understand the context of the impact of the impairment relative to the efficiency of the node across the entirety of the service group, that'll allow us to make really good decisions about every node's performance against its operational maximum capacity or throughput and the impact of the impairments on that. So that is the end of my presentation. I wanted to say thanks to the folks that contributed to this paper that we delivered at Expo this year: Alex, Wes, Mike, Maher, and Scott. So thank you all very much for your time today. I think I went over by a little bit, and I want to get out of the way because Mr. Wolcott always does a fantastic job of communicating and educating and talking about what's new and great in telemetry and technology.
I will work on getting Larry set up as presenter. So just give me a second, but go ahead, Larry. You can start the discussion while I do this.
All right. Well, let me get my deck up. First of all, I'm going to get a little bit of housekeeping. Here we go. Thanks. We got it, Woody. And let me go presenter mode. Are we full screen?
Yes.
Perfect. Perfect. Okay. All right. Thanks, Mike. Mike is a good friend, and we've worked on a lot of this stuff over the years, so it's always fun to present with him, co-present on these different things. Woody, thanks for having me. I met Woody over a decade ago, maybe 15 years ago, talking about a very similar thing. And I'm sure some of you here might have even been there. It's always interesting to go in the cable modem time machine here. We're going to talk about PNM and some neat things that are coming that might be interesting or maybe not. A little bit of housekeeping. We'll say Rocky Mountain chapter. I have a little bit of a plug in here so we get some collaboration points on the matrix, just like you guys do, and I always appreciate the opportunity to work together. So thanks for doing that, Woody. Huge Springbok fan. Best TDRs ever. Tracker Pro is my favorite. Okay, well, let's get going. I'm going to talk a little bit about PNM back in the old days, and then for those of you who remember, I've been around for a long time at Comcast. I worked on many of the tools that you might have used in the past, starting with the first operational tool we developed was Scout. You remember Scout? Maybe you even still use it. It actually hasn't changed much in probably 20 years. I think the first line of code was 2004. Yeah, I'm going to do a time check here so I don't run over like Mike did. Okay, got it. Then came Flux. For those of you who remember Flux, this was a really intriguing but strangely complicated and difficult thing to actually use and operationalize, right? And so we have impedance and reflections and standing waves and ripples and ICFRs and all these things that came out of that. And so I promise you guys this is actually a very technically rich subject, but I'm not going to go too far deep in the rabbit hole, and I'm going to keep it pretty lighthearted. There's a lot of technical complexity here, but the intent of this is not to show you how smart I am or Mark is. Or Mike. That's not the point. I'm actually not very smart at all. But I do want to cover some of the basics, right? Coaxial cable transmission lines. They work because they have a nominal impedance of 75 ohms. And there's a lot to that, but in lacking a 75 ohm impedance transmission line, some of that energy reflects, it bounces back at that interface. And that's the return loss and creates a reflection. You're going to hear about how the mechanical TDRs use that to give you a TDR distance and help characterize what the kinds of problems are, which is killer. And we still need that technology to actually go localize and fix these problems. So this is pretty neat that we get to talk about these in the same conversation. So you have an impedance mismatch and it creates a reflection. And when you have multiple reflections, which invariably you do because nothing is perfect 75 ohm impedance, it creates a standing wave. And you're used to seeing these this amplitude ripple in your spectrum analyzers, right? That's caused by a standing wave. Hey, Woody, are you, is that you with the mic on?
I apologize, yes.
No problem, got it. So standing waves and amplitude ripple. Okay, so that's all really interesting. And why do we care about that? Because we've been looking at ICFRs and ripples and all this other stuff for over a decade now, and we fully understand that. Well, let's talk about the basic physics. Again, not to sound too smart, because it's not that complicated. Any of us who have ever thrown a rock into a pond, you understand the basic principles of a wave theory, right? Like, if I know, it gets interesting when you apply math to it, right? If you understand the surface tension of the water and the temperature, and you can apply some principles of thermodynamics and wave theory, you can actually, if you can precisely measure the wavelength of the ripple that you cause in the water and the magnitude of that, and you have enough of the other information, you can very precisely tell how far away the rock landed in the pond and how big it was, right? So now all of a sudden, things get really interesting. And the underlying principle is we can very precisely measure the amplitude and the wavelength of the standing waves, so that now we know all of the other constants in our transmission lines, the velocity of propagation and et cetera. We could start to use that information to put together a picture of what the problem is and how bad is it and where is it, just like the rock in the pond concept. Now this is that I really promise you I'm not going to go into all of this, but the idea here is this is kind of the secret sauce about how it all works. The adaptive pre-equalizer in DOCSIS, this is the transmitter in the cable modems. It's able to adapt to the things that it sees wrong, right? So if there's a rock in the road and it creates a reverse rock in the road, you can back engineer that signature of the rock in the road to say where the rock is and how big it is, right? So that's a really simple way of putting it. But the new stuff with OFDM and OFDMA has, suffice it to say, looking at this block diagram, a much more sophisticated mechanism for telling us the same thing. And if you've been paying attention to OFDM and OFDMA, we're now operating at 50 and 25 kilohertz subcarrier spacing. These are very finely spaced channels, not just a big 6.4 megahertz or 6 megahertz chunk, right? So with that finer resolution comes much greater sensitivity and measurements. So in that whole academic exercise, in order, the reason that you haven't seen any of this yet is because it actually doesn't work right out of the box like the old stuff did. Pre-equalizers, like we saw in Flux, would give us ripples, and remember we tried to go through and say, hey, if you can count the number of ripples and divide that by the velocity of propagation and megahertz and whatever, you can tell the distance. Now that's all true, but it's really hard to do and make use of it because you don't really know where these distances are coming from and going to. And using a TDR, metallic TDR out in the field, you really have to be paying attention to which direction you're shooting and what's terminated, or right? Like otherwise you start to see reflections of reflections and splitters and all kinds of other stuff that might not make sense. So there's some digital signal processing we have to do to remove a lot of the stuff that we see before it's useful, and we got that all worked out. And then there is some time domain shifting, and on the right is what would hopefully look totally unfamiliar to you. You're like, what is that? There's all these peaks. Now when we do this digital signal processing and we time shift it and rotate the phase to a normal, not trying to sound smart, that's just math jargon for fix it. When we fix the signal on the left, that's starting to look a lot more like a time domain reflectometry reading, right? And it's essentially becoming to be the same thing. I mean, there's differences from where to what, and reflections and all that, and the mechanisms are all the same, but how you determine what to do about it is where things get complicated. But there are some other interesting things you're able to see on this. In the graph on the left is what noise looks like in the equalizer components. Now, this is not RX-MER, even though it looks similar, right? I see a channel response and I see noisy looking signatures. In the channel estimates, it's a little bit different because we have a Fourier transform and we can do time domain analysis of that. That's what you're used to looking at in a TDR, right? Time is the T. So now we're able to do this really sophisticated signal processing. The point of this slide is to say if you have noise in the channel, it diminishes our ability to do time domain analysis, right? Like normally I would see a peak sticking up at a distance when I have something that's not correct. In this case, the noise creates this grass-like signature in the time domain that makes it pretty useless and it even hides actual problems that we're looking for. So that's just one of the observations. And of course, another one, and this is a side effect of the Fourier transform, is when you have a significant tilt within the channel, which of course we do, it basically has an exponential one-sided decay of the noise floor. In this case, it's not, even though it's a 12 or 15 dB a tilt in the channel, it's still useful, and it doesn't really cause many problems in this case. So I'm going to move on a little bit. The question you might be asking is, all right, Larry, well, we've been doing this for a long time. Why go through all of this trouble, right? If I can use it fundamentally like it is, well, if you go back in the time machine it was probably 10 years ago when the very first Scout Flux came out, once you do all this digital signal processing to fix the phase rotations and normalize everything so that everything can be compared relative to other devices on the node. This is where the digital signal processing magic happens. And this, I'll tell you, this was the very first Scout Flux node that we ran years ago. And this was a really defining moment for me. What that means is when you have all of the signals from the modem and the equalizers able to be directly compared, I can take two signals that are very similar, like if you and I share the same reflection characteristics, meaning like let's say you have a damage to a feeder cable or a tap that connects my house and Mike's house. When I take those signals and directly compare them with digital signal processing, they actually cancel each other out, leaving a nice flat signal or a high match. And when I might have two signals that look similar, but they aren't the same, when I compare those directly with digital signal processing, they amplify and cancel. It's a constructive and destructive process. And the match is not at all there. So it's just a really accurate and precise way of matching signal characteristics caused by the plant to determine where the problems are. And in this case, you can see the colorization of the modems where we did this very first match. Okay, this isn't, oh, my levels are off. This is, you know, the fingerprint of the impedance characteristics of every little connector are shared by this bunch of modems. And think about the potential power in that, right? You can think about it as having a mini TDR embedded in every one of your cable modems. Now, you can't use that in the same way you can use a normal TDR, but very, very significant benefits if you figure out ways to do that. So going back in the eTDR, we call it the equalizer time domain reflectometer. This is similar, but a little bit different than a TDR. Remember back in the old days, we used to say, you count those number of bars sticking up to the right and multiply each one by 85 foot. And this was really a limitation of the technology at the time. And that's really how it worked. Multiply that by the distance off to the right, and that gives you the approximate distance within 85 feet, which, even with math tricks to do parabolic interpolation, to get it within a couple extra feet in one direction or the other, it did work that way. It does still. But you have a pretty limited resolution, right, at 85 feet per bar, and the sensitivity of that was, it had to be something pretty far out of whack in order to see it. And a lot of things can happen in an 85-foot chunk, right? So there's a bunch of problems with that. It was very useful when we turned it on because we found a lot of things that were just kind of swept under the rug over the years. But after you go fix and clean up all the big stuff, you ended up chasing, things that might not have been that important. So in this example, the example on the left at 85 foot per tap resolution, right? Like you can see things that are important, but the usefulness is somewhat limited because of that resolution. The exact same node and customer equipment on the right is a whole different picture, even though it's telling you the same thing. The new version on the right has very high resolution. Look how tiny those little bars are sticking up. And look how far down into the noise floor you can see them. So now, instead of, if it's a significant problem, we can see it, and it's shared by a bunch of customers, and it's isolated to a long enough span. That's the use case for the left where we have been living for 10 years. Now, the new OFDM and OFDMA high resolution version of that is a lot more like a TDR that you're used to looking at. So the resolution is either roughly 2 to 4 feet, not 85 feet, 2 to 4 feet, and significant improvements in dynamic range and sensitivity. So much so that you can now see reflections caused by things that aren't necessarily a problem on your plant. And so we'll talk about that. The sensitivity improvement is where the mind shift needs to happen. If you look at the signature on the left, this is the frequency response. I didn't scale it right on purpose. This is an OFDM channel at 94 megahertz wide. the clue here is if you look at the Y scale, it's 1 dB per division. Now, if you zoom in really close, because of the new high resolution offered by the OFDM and the OFDMA, and the sensitivity and the dynamic range of that very fine equalizer, you can start to see little teeny tiny things in there that are caused by normally occurring impedance mismatches on your plant. It's totally normal, right? Every connector, the ground block, the tap, right? The back of the cable modem, every one of those is not a perfect 75 ohm impedance match connection. And every single one of those creates a very tiny little reflection. Now we're able to see those teeny tiny little reflections and put together a map of those interfaces and how they're connected. So hopefully you're going to hear a little bit about this in the way that the metallic TDRs work is exactly the same way that this works in this regards. Because it's digital signal processing, I have the signal itself now has an understanding of the phase component of that reflection. So if you have a interface on a plant, just say a connection to the tap, it has a little reflection. If there's water in the tap, it changes the properties of that reflection in a way that you can actually detect. Just like a metallic TDR, the phase is shifted based on the type of the cause of the reflection. And it's there's issues with it, and it's not super perfect. But for example, when there's water present, or simply an open circuit versus a short circuit fault, in those two binary examples, it's incredibly good at it. You can get, within 15 or 20 degrees of phase accuracy to determine if it's an open circuit fault versus a short circuit fault. And another interesting side effect that we learned from this reflection analysis is that it's kind of a little obscure, but I'm going to go there anyway, is that OFDM and OFDMA have a construct called cyclic prefix. This allows the receivers to have a buffer that protects them from echoes that are caused by things in the network. And intentionally, we built that cyclic prefix buffer to be 512 points long. And now that we're able to do this really precise analysis of the echoes that are actually hitting the cable modems in the RPDs, now we can do really accurate analysis of those cyclic prefix to say, wait a second, we really don't need a cyclic prefix of 512. We can reduce that to 256, and in some cases even shrink it all the way back to 192, because it's not super obvious on this chart, but the threshold to operate a 4096 QAM, 2048, or 1024 QAM quadrature is that those green, yellow, and red bars there. In this case, on this node, we can recover about 5% capacity that's being completely wasted on this cyclic prefix. And it was intentionally built to be safe, but in most cases it was too safe, and we now know that we can reduce it. So just like we're doing it now, I'll tell you, you'll start to see a lot of cyclic prefixes going from 512 to 256. You're going to get about a 5% performance improvement, throughput and bandwidth improvement from that, throughput and bandwidth. And then as the opportunities and needs arise, we'll start to do more automation on cyclic prefix tuning, just like we did profile management with PMA. So cyclic prefix tuning might become a part of PMA, for example. So it'll be automatic and adaptive based on the environments. So as I alluded to, I'm going to get to the punchline. I'm going to pull us out of the rabbit hole of technical details. And what's the punchline? Larry, why do I care about ripples? We really don't like chasing those anymore. We found all the gold in the hills, and now it's a lot of work. Well, because ripples, if you have a high enough sensitivity and dynamic range, are caused by basically everything that you're connected to in every cable on our network. And in this case, when you can mathematically subtract out the ripple caused by each cable and have accuracy between 2 and 4 feet, you can start to automatically create a network diagram to every single house in home wiring, MDU, anything connected to a cable. Yep. So in the old low resolution version, this is a node where there is a trunk, and the trunk happened to be over a bridge, and it was in Florida. Still, I don't know if it's fixed or not, I should go check, but in Florida. And if you look in a low resolution perspective, you can see a ripple, and the ripple math works out to the place. So the new version of that is this to the right. You can see that same, in the time domain, you can see that same echo. That's the furthest one to the left and how far out it is. But you can also see not just the broken cable, but the amplifiers, taps, the lengths of cable, and even the drop cable to the houses that are individually connected to it. Yeah, it's pretty amazing. And so we have to do a new mental model that, using reflections to find things broken on the plant, you know, we understand that pretty well, but now we're able to use reflections to find things that aren't broken and very accurately map them out and locate them. So that's the new frontier with P&M technology. And so I'm at 25 minutes, which is ahead of schedule. And that's good because Mike ate up a bunch of my time. Just teasing, Mike, I appreciate you. There were some co-authors that contributed to this work, Cable Labs, Prompt Link and Oceanside. These guys are really fantastic if you haven't had an opportunity to meet them. Broadcom, Mike Spalding here at Comcast, and of course my peer reviewers, Ron Ranick, Alberto Campos, Roger Fish, Tom Williams. The best of the best, and the founders of P&M. And so I'm really privileged to be here giving you an update. And you can expect to see some of this stuff coming in the tools in the next year or two to come. I'm very excited about that. So Woody, that's it for my presentation. And I am done. Hey, Woody?
Once Woody gives me control, I will get on with the presentation.
All right, let's see, maybe I can do it here. Yes, let's do that.
All right, that sounds great.
Very good.
Hey, thank you, Larry. Well, my name's Paul. I'm with Springbok Instruments. I want to just do a little bit of housekeeping and thank Mike for his presentation. Thank Woody for being our MC today, and thank Larry for teeing me up and talking about MTDRs. Now, we don't have time to do a full training session, but what I'm going to do is pull up a screen mirroring program, put the TDR on screen. We can do kind of a little miniature presentation on Springbok TDRs, kind of what makes a TDR, metallic TDR tick. And make sure you stay till the end because we have a raffle. I'll spin the wheel of names and someone will go home as the lucky winner. So with all that being said, let me get this screen mirroring program up and running. All righty. So, if I didn't say it already, my name is Paul Shea. I'm with Springbok Instruments. We are a TDR company based in Omaha, Nebraska. We make, design, manufacture, code our app, populate our circuit boards, do everything in-house. So if you have any questions, don't hesitate to give us a shout at any time in terms of functionality, anything like that. So like I said, unfortunately, we don't have time for a whole TDR training session, but we kind of do a mini session and then make sure and stick around for the raffle. So a TDR, metallic time domain reflectometer. Like I always say, what makes it tick, right? So the science behind using a TDR is very comparable to radar. And a lot of times you might hear people refer to using a TDR as cable radar. So what makes it tick is the same basic principle as a radar gun. Let's say someone's using a radar gun to detect speed. We use a TDR to detect distance. And how that physically works is the TDR itself sends out a pulse of energy, and it is based on power when you're using metallic TDR. There is other TDR types that use frequency to measure anything, any cable or anything with a metallic center conductor under test. But for our purposes today, we're basing this on time. So what the TDR physically does itself is it sends out a pulse of energy down the cable under test. It hits any events, faults, impedance mismatches, and it reflects that pulse back to your instrument. And it converts how long it takes for that pulse to reach any of those events, reflections, or faults, and it converts that time to distance, hence time domain reflectometer. So what is the beating heart of any TDR? And the beating heart of any TDR is the pulse width. Now, for our purposes today, we're going to talk in nanoseconds, how you measure your pulse width. But in other applications outside of cable, if you're looking at HV transmission lines or medium voltage transmission lines that are going, multiple miles, you might be measuring in microseconds instead of nanoseconds. A lot of the range we see in cable television, we're going to be measuring in nanoseconds. So we'll stick with that today. So like I said, the beating heart of the TDR and what makes it tick is that outgoing pulse width, that pulse of energy that's based on power. Now, Larry did mention a little bit about frequency, kind of our 75 ohm standard across the line. And since this pulse is based on power and not frequency, it doesn't of everything that is on screen for the TDR. So let me just zoom out a little bit here and get a waveform up and going. All right. So first thing we always talk about, like I said, is pulse width. That is the physical pulse of energy leaving the TDR, traveling down the cable under test, and reflecting back to the TDR to give you readout of your events on screen. I don't always like to jump to the conclusion to call everything faults, because just because you have an event does not mean it's a fault. So we can kind of capitulate on what it might mean to have an event versus a fault, but I always like to start with events. And when you read a TDR, I always say read it left to right like a book. So you kind of start on your left and you go to your right and read down the line. So as you can see on screen, we have a recalled waveform. And when you look at your primary waveform, you can see your outgoing pulse width is this upward leading inflection. You have some events along your span, and then you have the upward inflection signifying an open, which is the end of your cable at 468 feet. So like we say, anytime you use a TDR, read left to right, and that will kind of give you any kind of data input that you're looking for. So just a couple housekeeping things. Anytime you use a TDR, you always want your leading edge, you always want your cursor set for your measurements, your first cursor, the cursor that events are measured from, at the leading edge of your outgoing pulse width. So depending on where you place cursor, this will give you your best footages. So When you're using a TDR, your measurement cursor 1 to cursor 2 will give you a footage to, for this instance, a barrel splice, cursor 1 to cursor 3. Or, depending on which TDR you're using, you can, in this instance, zero out your footage for a jumper cable. So that way you know your measurements are correct every time. So all that to say this, pulse width, like I said, it's kind of the engine which drives the TDR. Since all cable has loss and events that are further away are going to be smaller in amplitude, pulse width dissipates over distance. Events, like I said, further away, smaller in amplitude. So how do you mitigate the chance for error? Either one, within the launch of your TDR, all pulse widths have a blind spot, and all TDRs and all cable has loss. So as that pulse width travels down the cable, it reflects back, it dissipates over distance, right? So using a jumper cable can help you kind of minimize the chance for error when you are using a TDR within finding any events within that launch period. Also, I know that this is, kind of something that is required for repairs and replacements within some systems, but shooting your cable bidirectionally can also minimize the chance for error, because pulse width dissipates over distance. Events that are further away, smaller in amplitude and harder to see. When you shoot your cable bidirectionally, shoot it from the other direction, you are putting your TDR launch closer to any events, so the amplitude of that event should be larger. So like I said, as you read your TDR, you read left to right like a book, and pulse width dissipates over distance, events that are further away, smaller in amplitude and harder to see. As you increase your pulse width, you're sending a higher energy pulse down the cable under test. It will create differences in amplitude for your events and allow you to see smaller events at further distances with larger pulse widths. Keep in mind that when you increase pulse width, you increase your blind spot. So as you can see, at 2 nanoseconds, we have a fast leading edge, return to baseline, and a small blind spot. When you increase that to 20 or 50 nanoseconds, let's say, you create a larger blind spot. So that's where shooting the cable bidirectionally can be very useful. Okay, let's change this back to 2 nanoseconds just to keep things the same. The next thing we always talk about, vertical gain. Vertical gain is just a representation of zoom. So since on all of our TDRs, which are touchscreen TDRs, you have your primary waveform and you have all of your corresponding magnification windows showing you footage and DBRL, you have a split number designation. So in this instance, you are looking at your primary waveform at 4 times magnification. Any of your corresponding zoom windows are 16 times magnification, right? So if I bump this down, you can see 1x, 4x, right? It changes the amplitude of your events. You can still see them magnified 4 times in any of your corresponding zoom windows. As you increase that up to, let's say, 4x, 16x, you can see the magnification of your events grow much larger, right? And in your magnification windows, it is up to 16 times. So what you're doing is stretching the vertical amplitude of your waveform. You're not physically changing any attributes on how the waveform looks on the TDR. all you're doing is just creating a margin of zoom and stretching that vertical amplitude. So vertical gain is a very advantageous tool. Anytime you're looking for events on a TDR, small damage you might not physically see, you know, start adjusting vertical gain. So similar to pulse, there is no magic number. Every instance of looking at a span or a cable under test is going to be different depending on what you're looking for or looking at. So similar to pulse, I always start on the lower levels of vertical gain and increase as you need. Something to keep in mind, anytime you're using a TDR, when you're using vertical gain, if you use these higher levels of vertical gain, since you are stretching the vertical amplitude of that waveform, what you are doing is putting excess noise on the cable that is not necessarily there. So, you know, all TDRs have, you know, different noise signatures for either RF, AC, so on and so forth, water, whatever it may be. When you increase vertical gain all the way up, it puts excess noise on the cable that's not necessarily there. So, you know, take that with a grain of salt when you're using vertical gain. Know that it is a very useful and helpful tool when you are diagnosing, you know, any kind of damage on your plant or events on your plant. But keep in mind that these higher levels of vertical gain, they do put excess noise on the cable. All right. The next couple features are pretty straightforward and simple. Range is just a function of showing you how much cable you're looking at on screen. Okay, so if you range all the way down, the waveform that we've been looking at all day has become shrunk on the, you know, the micro scale. You can see your outgoing pulse width at the beginning of the cable. You can see it spliced, but you're no longer seeing the end of the cable. So as you range out, you can see more events along your span. And if you range out further, you can see the end of your cable at, you know, 464 feet. So after you've gone through pulse and vertical gain, if you're not seeing the end of the cable or an open you've created, just range out. Simply put, it might not just be on screen. That kind of brings me to my next point before I talk about VOP. I'll take a couple minutes to talk about VOP and then we'll get into the drawing. But something that's really useful about any of our TDRs is when you have a, you know, a digital TDR with touchscreen and all that information is stored within the screen. We also have our store feature, which allows you to store the whole entire waveform with the push of a button. So since I'm looking at a stored waveform, I'll just go back to go live. And anytime you're using any of our TDRs, there is a store button. And that store button allows you to store all the information you're looking at on a specific span with just the push of a button. So let's say you plug into a span, you know, a feeder cable and it's 1,700 feet long, a trunk run, whatever it may be. You want to put your customers back online as soon as possible. What any Springbok TDR allows you to do is store the entirety of that information regardless of what's on screen. So let's say you plug into this feeder, it's 1,700 feet, plug it in, you hit store. What the TDR will do is store all of your pulse widths, it will store all of your vertical gains, it will allow you to range in and out from a stored waveform. It will allow you to change your horizontal position, manipulate VOP, and continue to use auto search, which is kind of our test wizard as it is. So when you hit that store button, you don't have to go to 2 nanoseconds and hit store, go to 20 nanoseconds and hit store, change your vertical gain back and forth. Anytime you're using you know, Springbok TDR, you get the entirety of information stored with your push of a button. And what that allows you to do is put your customers back online, and then you can diagnose what you need to from that stored waveform. You can either do it on the TDR itself, or you can do it on our app, which is called Tracker View. All of these TDRs are touchscreen and Bluetooth, so you can simply just send a waveform from your TDR to your phone, and then you'll have the same layout to allow you to control the cursors, change any functionality you might need, all from that stored waveform. So if you're using our TDRs in the field, it's very advantageous, and it is a time saver for us, for the customers as well. So just a little food for thought. All right.
By the way, my audio's back, Paul.
Okay. Hey, no problem.
Yeah, it was strange. I had to toggle off and on the audio for it to start working again. But I'm back.
Yeah, you never know sometimes, doing these presentations with GoToMeeting or Zoom or Teams, sometimes it's a mystery why things don't work. Alrighty, so talked about pulse width, vertical gain, range. Next, I want to talk about VOP. So VOP stands for velocity of propagation, and it is a representation of how fast anything with metallic center conductor, for our purposes today, cable in our plant, carries a signal in comparison to the speed of light. So the speed of light in a vacuum is 186,000 miles per second. What that means is if you have a cable in your HFC network that transmits a signal at 87% VOP, that cable is transmitting a signal at 87% the speed of light in the vacuum, right? For our purposes, for our customers' purposes, it's an instantaneous transmission of information, right? Now, obviously, when we talk about fiber, we are transmitting information over glass through light, so that's going to be a little faster, but there's a reason there is so much HFC network in our plants, and it has stood the test of time. Durability, obviously, and the fact that we can deliver, pretty crazy signal speeds through such a durable network, right? So why is VOP important when you're using a TDR? VOP is important because the more accurate you can be with VOP, the more accurate your measurements are going to be when you're using a TDR. So how do you determine VOP, right? Throw a bunch of numbers at you and you say, that's great. How am I supposed to know what the specific cable type is? There's a few kind of surefire methods that I always use. The first is, what is the manufacturer recommended VOP? And then you say, how am I supposed to know the manufacturer recommended VOP? So we built in a creature comfort to all of our TDRs, which is the standard cables list. Now, these are all about 70 different manufacturer recommended VOPs if you know the cable type. And I understand that's part of it too. But let's say we go to MC squared 650, 93%. You click that, it takes you back to the main screen. The TDR will change the VOP to 93%, and you know your measurements are going to be accurate. Okay, so always use your manufacturer recommended VOP list. If you're not certain of, or the TDR you're using doesn't have the manufacturer recommended list, I know some TDRs have a little plastic sheet, some have it built into them. If you're ever uncertain of what you're looking for, you can just Google it. Most of these are, pretty straightforward from the manufacturers. They want you to know the VOP. Now, I've heard people say, well, VOP can change from different manufacturing runs, or it might be 90% for this manufacturing run or 93% for the next manufacturing run. All of these manufacturers are pretty consistent about maintaining specific VOPs for their specific cable types. If you know the manufacturer recommended VOP, I would just use it. More likely than not, what can change VOP is the variance of time, age of the cable. Is it aerial? Is it buried? Has it been exposed to the sun, baking in the Arizona sun? Is it going through heating and freezing in Nebraska? So those indicators are more likely to change VOP. But even there, you don't see a drastic swing, a couple percent here or there. So if you know the manufacturer recommended VOP, just use it. It's going to get you pretty close for measurements. Okay. The other way you can determine VOP is kind of backdooring it and using a known length of cable. So let's change this back to 87%, and then go back to looking at this test span that we've been looking at. So a way you can determine VOP is by using a known length of cable. So this is just a test span that we have in our offices here at Springbok. What you can do is simply take one of your cursors. Let's get that off screen. And I know that this span is 478 feet, right? And you measure to the end of your cable, and you can see, well, the measurement's not exactly right. That means my VOP must be incorrect. So let me bump this up a little bit. All right, 475.4 feet. Then I know the VOP is 87%, right? So the same scenario can run out if you have a piece of cable in your plant, let's say that you know is 800 feet. You know it to be 800 feet because either the plant map's accurate and that's what it says, or you fixed it before and you've already determined this piece of cable is 800 feet. What you can do is pull the end of the run, create an open, take your cursor, put it at the end of the run, and then manually adjust your VOP until the footage on your screen matches what you know to be the known length of cable. So that's another way to backdoor VOP. And then the last way that you can always determine VOP is to shoot your cable from both directions. So I know previously we talked about shooting the cable bidirectionally to minimize the chance for error within that launch period with the outgoing pulse width. Another thing that you can do to find the true distance to events is just shoot your cable from both directions. So as long as you have the VOP set the same going both ways, you shoot your cable from direction A to B and mark your fault. Let's say 90% is the VOP. Go to the other end of the cable, put the TDR at 90%, shoot your cable from direction B to A and mark your fault. And if you mark both of those faults and have the VOP going, you have the VOP on the same figure going from direction A to B and B to A, mark both your faults and measure between them, that will put you on the true distance to the event every time. So when it comes to VOP, velocity of propagation, the more accurate you can be with VOP, the more accurate your measurements are going to be. So use those three tricks. Use the manufacturer recommended cable list, use a known length cable, and just shoot your cable bidirectionally, mark your faults, measure between. If you use one of those three tricks, more likely than not, you are going to have accurate measurements with your TDR to any events along your plant. Okay? That is the majority of what I wanted to talk about kind of within a mini training session, talk about functionality. I do want to talk briefly about our software and our app, and then we will do our drawing. So I know I did mention briefly that all of our TDRs are touchscreen and Bluetooth devices. The really nice thing about having touchscreen TDR is ease of use for functionality. Even if you've never picked up a TDR before, having all that functionality featured within the screen just allows you to press buttons and change functions. You don't have to know which button moves which cursor, which button changes VOP or pulse width, vertical gains, so on and so forth. It's all laid out for you on the screen. So even if you're relatively new to using a TDR, it is very simple and easy to use, very intuitive, right? I want to talk about our app quickly. Since all of these TDRs are Bluetooth and touchscreen, we do have an app that goes along with it. It's available on the Comcast store. It's available on iOS for any iPhones or iPads, and it's available on Android. So you can simply put, like I said, store all of your information with the push of a button. And it's going to store all your pulse widths, all your vertical gains, the whole length of cable, regardless of what you're looking at, allow you to change VOP from that stored trace. And what this does is allow you to send it either to your PC or to your phone, and then you can diagnose from your phone or your PC like you were live on the cable. So that is very, very useful and very advantageous to use in the field. Like I said, the more downtime we can eliminate for our customers, the better. So, you know, when you plug into a span, you can just hit that store button, store the information, put your customers back online. Then you can diagnose from your phone, from the TDR itself, or from the PC. So if you are using one of our TDRs in the field and you are not using the storage function and the app and the software that goes along with it, I would highly recommend downloading it. Like I said, it's called Tracker View, all one word, available on PC from the Comcast store, iOS and Android. So that is, by and large, everything I have kind of talk about. Wanted to definitely talk about a little bit of functionality and, you know, just talk about making the most of using your TDR, as well as, you know, using the technology that is at your disposal to make your jobs easier and you know, make our customers happy. So
Thank you for that, Paul.
Yeah, no problem.
And thank you for those that stayed on for the raffle. Need to be present to win. Gave quite a few names. I captured them at a given point. So if you came in, if you left before or came in late, your name might not be on there. I'm sorry about that, but it was impossible to wait till the very end because there was like a lot of names. so just a couple of points about TDR, if I may. I remember as a technician when I was on call, we had a shared TDR. I made sure I had it. I made sure I had it because I wasn't going to go do extra work or guesswork exactly where a plant fault is. I wanted to know exactly what pole to climb or exactly you know, where to dig if I had to dig. So if you have access to a TDR, use it. Get it in your hands, play with it, get familiar with it, learn how to use it. It's an excellent tool, and no tech should be without one, or at least be trying to troubleshoot without one. And if it's underground, don't necessarily blame the TDR if the footage seems way off. I had a situation where I had a tap, I think, across the street from where I was connecting the TDR, and the design showed a cable direct going straight under the street, and over there it didn't, because it was like 130, 140 feet, which was, it must have gone down the street and then crossed somewhere else and then came back. So if the distance seems way off, don't necessarily blame the TDR. It could be something else.
Oh yeah, and
I will be quiet about it. I'll let you go about the raffle.
Oh, no problem. That can all change. Yeah, and Woody makes a really good point. If you have a TDR at your disposal, use it. The more you use it, the better you'll get using it, and the easier it will be to you know, find any events you might need to and you know, fix damage. So, alrighty. So we got the wheel of names for the raffle. This is a gift card, and I'm not sure exactly to what the gift card is for. I'm sure Woody would be able to give us some clarity there.
Yeah, just for staying behind and attending your presentation.
Okay, wonderful. All righty. So we got the wheel of names. We'll give it a spin and we'll see what it lands on.
So if your name's called, just tap in the chat, confirm you're still here.
All right, it came up for Paul Graves.
Paul, are you still here? Let me see. Let me look at attendees and see if I can see if Paul is still on. Nope, don't see him. So you're going to spin it again.
All right, let's spin it again.
Greg Brown. Where are we? Oh, Fang? Let's see. Who are you on? Nope. I'm sorry. We had a lot of people drop off, so I've not seen it.
We'll get a winner.
case I'm missing you, please tap in the chat so I can see you're there. Let's see.
We'll get a winner here eventually.
Sorry, son, this is covered. Oh, Greg Brown. Greg, are you still on? Greg is still on.
All righty, we got a winner.
Greg, I hope you can hear me okay. So how would you Paul, how would you like Greg to contact you?
He can just he can email us. I'll just throw my email in the chat, and we can make sure and get him his gift card that way.
So congratulations, Greg. Hope you're hearing us, and Paul's going. If you have any, if for some reason you don't get in contact with Paul, hang on a second. I've got a question here. Let's see what this says. Oh, okay. No, that's you. Okay. So reach out to Paul at springbockinstruments.com. And if for some reason that doesn't work, you can always reach out to me, wfcash@comcast.net, and I'll put you in touch with Paul. So thank you, everybody, for the outstanding presentation today. It was we had an awesome lineup, and thanks for Paul for presenting here or doing our virtual tabletop. This is the first time we've attempted to do a virtual tabletop. So Paul, you will always be first.
All right.
Yeah, and we hope to try this again next year, maybe expand a little bit. So thank you, everybody, for your attendance, and thank you, Paul, for the raffle, and thank you to Mike and Larry for the just awesome presentation. Everybody have a wonderful day, and one more plug. We do have a TDR presentation by Chuck Phillips on January 7th. So feel free to join. We'll get into some really nitty-gritty details about how to best utilize your metallic TDR to get you to where you need to be and make the repairs you need to make. So thank you, everybody.
All right. Thank you, and appreciate it, Woody. And I hope you can tune in for Chuck's training coming up in January. Make sure and ask him very hard questions. He's been working with TDRs and in the industry for about 25 years. So we always like to try and stump Chuck if we can. So
yes,
I appreciate it.
I like that. Let's try to stump Chuck. Okay, thank you, everybody.
Time. Thank you.
Bye.
Bye-bye.